This glowing data network represents the modern JavaScript ecosystem. At its center is Axios, an HTTP client handling over 83 million weekly downloads across front-end frameworks, back-end services, and enterprise applications. Look at this dependency graph. It highlights the core paradox of a recent attack. Threat actors compromised versions 1.14.1 and 0.30.4 of Axios without altering a single line of its actual source code. If you run a traditional diff-based code review, you find zero anomalies. The core codebase remains perfectly clean. The intrusion occurs down the tree. The attackers injected a fake transitive dependency named plain crypto.js version 4.2.1 directly into the Axios package sequence. Security teams audit parent source code. This attack vector weaponizes the implicit trust in those parent packages to execute hidden attacks within the subnodes. The 18-hour deployment followed a strict predetermined sequence. This timeline begins on March 30th at 05:57 UTC. The attackers published a clean, benign version of the plain crypto.js package to establish a baseline in the registry. At 23:59 UTC, the attackers published version 4.2.1, this time containing the malicious payload. On March 31st, the execution phase began. Using the compromised credentials of the primary Axios maintainer, the attackers published the poisoned Axios versions just 39 minutes apart. Investigators found the attacker first changed the maintainer's registered email to a Proton mail address before using a long-lived classic NPM access token. This allowed them to publish directly to the registry, bypassing the project's GitHub Actions CI/CD pipeline entirely. By utilizing direct registry access, threat actors can circumvent the automated security controls built into upstream development pipelines. The attack is triggered automatically during installation. It weaponizes NPM's native post-install lifecycle hook, executing before the developer ever interacts with the application. This schematic outlines the infected package directory. The lifecycle hook immediately launches an obfuscated Node.js dropper called setup.js. Once the payload drops, the malware initiates a forensic cleanup. First, the dropper deletes its own post-install script from the directory. Next, it removes the original package.json manifest, eliminating the malicious hook that triggered the download. Finally, it renames a dormant package.md to package.json. This file contains a clean manifest, effectively replacing the evidence. When post-infection environment audits or standard vulnerability scanners inspect the directory, they find only the clean manifest, reporting no signs of tampering. Combining native lifecycle hooks with real-time manifest manipulation creates an execution chain that leaves no static footprint for investigators to find. This flowchart illustrates the Node.js dropper's core capability. It branches its execution path based on the host machine's operating system. On macOS, it runs an AppleScript payload to fetch a compiled C++ remote access Trojan. To maintain stealth, the script saves the binary to the local cache folder, com.apple.act.mond, modifies its permissions to make it executable, and launches it in the background via ZSH. The initiating AppleScript is then deleted to cover the malware's tracks. On Windows, the malware copies the local PowerShell binary and renames it to masquerade as the Windows Terminal app, wt.exe. It executes a VB script from the temp directory to pull down a secondary PowerShell RAT script from the external server. Windows is the only target where the malware establishes persistence. It creates a batch script that refetches the malware on every login and adds a registry run key to ensure the script triggers. The PowerShell RAT can execute arbitrary DLLs directly in memory, avoiding the need to write new, detectable files to the disk. Immediately upon launch, the RAT performs system reconnaissance, enumerating user directories, mapping drive routes, and listing all running processes. The dropper adapts its evasion and persistence mechanisms to exploit the specific architectural characteristics of each target operating system. On Linux, the attack utilizes the exec-sync command to download a Python-based RAT. It saves the payload to /temp/ld.py and executes it in the background using the nohub command. Unlike the Windows variant, this Linux RAT lacks a persistence mechanism. It does not survive a reboot, suggesting the attackers prioritize rapid data exfiltration over long-term surveillance on Linux hosts. Despite using different languages, all three payload variants connect to a centralized command and control infrastructure. All 3 RAT implementations utilize an identical 60-second beacon loop to check for further instructions. This is a unified routing mechanism. The C++, PowerShell, and Python variants all send HTTP post requests to the same external server. The server uses endpoint differentiation to sort the traffic. macOS requests route to the Product 0 URI. Windows requests route to the Product 1 URI. And Linux requests route to Product 2. This setup allows a single C2 endpoint to multiplex its traffic and serve platform-appropriate responses to all 3 operating systems. This consistency, the identical beacon intervals, shared command sets, and unified message formats, indicates a coordinated team working from a shared design document. The threat actors achieved broad multi-platform reach while minimizing back-end complexity through an elegantly multiplexed C2 protocol. Forensic analysis of the malware's architecture links this attack to an established advanced persistent threat. Analysis of the macOS Mako binary reveals significant code overlap with Waveshaper, a C++ backdoor used in previous espionage campaigns. Security researchers have tracked Waveshaper to the North Korean threat actor designated as UNC1069. The attack vector also spread through vendor dependencies. Packages like @Shodanai OpenClaw and @QQ-Browser OpenClaw QBot were found distributing the exact same payloads via tampered internal folders. State-sponsored actors are now weaponizing the open-source supply chain architecture to deploy espionage tools across the JavaScript ecosystem. Security teams should audit CI/CD pipeline logs for any automated installations of Axios versions 1.14.1 or 0.40.4. Services must be downgraded to the safe Axios versions 1.14.0 or 0.30.3 to remove the malicious dependency. To confirm an active infection, search your environments for these specific file paths: com.apple.act.mond on macOS, the fake wt.exe on Windows, and ld.py in the Linux temp directory. Network security teams must block all egress traffic to the command and control domain sfrclak.com. If any of these artifacts are detected, the host must be assumed compromised, requiring a comprehensive rotation of all system secrets and credentials. Modern supply chain security requires shifting focus from parent source code to monitoring the hidden lifecycle events that operate in the background.